Okay, so welcome everyone. Today we're happy to have Pauline Vielzeuf. So Pauline was a PhD student in Barcelona, and then she moved to Trieste in Italy for a postdoc, and now she's working in CPPM in Marseille. And she will tell us about cosmic voids and CMB lenses. So Pauline, you have 45 minutes roughly, and then we'll move on to questions. Thank you for accepting your talk.
Yeah. So do I have the sound okay? Can you hear me?
Yes.
Okay. So yes, hello everybody. So I'm Pauline Vielzeuf. So I'm a postdoc at CPPM, as Rodrigo just said. CPPM is a Center of Physics of Particles of Marseille that is based in this really fantastic national park that you can have a picture here. It's just to make a bit of commercial about it. And today I'm going to talk to you about something from nothing, and more in particular cosmic void as a CMB lenses. So this is like a brief outline of my talk. So first I will start to introduce you how do we do cosmology with cosmic void. Then I will show you the correlation of cosmic void with CMB radiation, and more in particular the CMB lensing signal, showing you then the methodology and the state of the art of in the field, and then I will present you the last analysis that we have been doing, trying to disentangle what is the sensitivity of this correlation to massive neutrino. So yeah, so brief introduction, what are cosmic voids? So when you're like observing basically the sky, what you're observing is the galaxy, the lights, the overdensity region of the cosmic web. And if you look in details of the cosmic web, you see that the galaxies are like clustering within each other, forming like a really overdense region, like clusters. Can you see my pointer, by the way? I don't.
Yes, we can, yes.
Okay, like clusters, filaments, galaxy cluster filaments, and in the middle of that, what you can see is this like really large regions that are like underdense regions that we call the cosmic void. So just to give a order of magnitude, an idea of the like size of these objects, it's like the order of magnitude is tens of megaparsec per age, which is much larger than the other object overdense region that we observe in the sky, and that's why until now it was quite complicated to use them statistically, because we didn't have enough observation to have like enough voice to use them in a statistical way to do cosmology. But nowadays, with like new observation like Euclid, LSST, and so DESI, and so on, we can hope to have a statistical power to use them as a cosmological probe. However, with respect to the other objects, like the overdense region of that we observe, usually cosmic void are like kind of tough to define in the sense that they are not visualized objects. So we have to give some, we have to put some rules to make a definition to find the void. For example, in this picture, you can decide to find your void to be this really large region that is like really surrounding by the filaments. Or you can say like, okay, I don't want all this structure in the middle, and I can decide to have like, let's say, put a threshold in my definition and say I don't want a void that is that has this structure and that they like split this void in 3 different voids that are much deeper. So as I was saying, so there is like different way to define the void, and that's why in the literature you can find a lot of different void finder, and this is an example on the right hand side of this slide. Like here you have like 4 different void finder. In this column it's like 3D void finder. So like 2 different 3D void finder, but you have other of them. One is just spherical void finder, so like identifying a spherical underdense region in our observation of simulation. The other is Zobo, which is like using more like a complex technique to identify voids. This is one of the most used nowadays in the void analysis. And the right-hand side here, you have like 2D void finder, because you can also identify void in a redshift slice, so like projection of under density in the line of sight, 2 different of them. And this is quite interesting because I'm going to talk about it later. These voids are actually particularly suited to do void lensing, to use voids as lenses, in the sense that since you are like projected the density field along the line of sight, they are like elongated objects, so the signal to noise of lensing signal will be a bit more, it will be higher than in a 3D case. Nevertheless, even though like all these voids are quite different, we can actually let's say picture them in a really identical way, in the sense that they present more or less the same density profile. And this is an example of what is the density profile of a cosmic void as a function of the radius of the void that you are like looking at. So the density profile is basically the 2-point correlation function. So the density that you have at a given position of the void center. So like in a x-axis here, you have the void center. So as you go to higher value, you go to further from the void center. And what you see is like you have this under density, so negative density with respect to the mean density at the void center. And then as you go further, and you reach the void radius, which is 1, you reach the mean density, and then you have this feature which is surrounding over density of the void that we usually call the compensation wall. Of course, this definition changed from one void finder to another, but the general feature, the general idea is more or less the same. Like the compensation wall will be more or less pronounced, but it's more or less the same for all of the void finder that we have. Another thing is that voids can also be considered as tracer of the matter field, the same way that we are using the galaxy or the galaxy cluster, the over density, computing the power spectrum of the 2-point correlation function. We can also use the void as a tracer of the matter field. And this is an example of the 2-point correlation function of void and void. So like you are like correlating void with like the position of the center of the void with the position of the center of another void, and in the bottom void and galaxy. So at a large scale, and you see you have a non-zero correlation function. So basically you can use this as a tracer of the matter field, the same way that you use the galaxy, modulo bias, of course. And also in the same way you can use them as lenses when you are doing gravitational lens, when you are doing weak lensing. So instead of taking galaxies, so instead of measuring the deflection of light at the position of galaxy, you can take your voids as lenses. And this is an example of the tangential shear measurement of a background galaxy. So it's like the distortion of light due to the fact that the void the light is like following the geodesics of the matter, and like so the galaxy in the background will be more oriented towards the galaxy, so toward the matter that it cross along the line of sight. If you look at the at this deflection of light at the position of a void, you are like expecting the light to be actually delensed, looking at the positive direction. And this is an example of this delensing effect in the measure in the dark energy survey. If I remember well, this is year 1 analysis of the dark energy survey. So this is like this gravitational lensing effect as a function of the radius. And you see that you have this negative signal at the position of the void radius. So the galaxy tends to look, let's say, backwards of the void, like to be oriented like in the other direction of the void center. And finally, voids can also be used in a different way than tracing the matter field. So you have like other way to use different void statistics to put constraints on cosmology. So I give you here an example, but there are like other of them. I cannot really give all of them. But for example, you can use the void size function, which is basically the number of void of a given size that you have in the universe. And this is an example. This is like actually a forecast that we have for the Euclid satellite. So you have like a prediction of the number of voids that you should have for different size of void or at given size of void. And it's quite interesting because by itself, cosmic voids, because statistically we are a bit poor, they are not really really strong in the cosmological constraint. However, they are like showing a lot of I mean, we are observing totally different objects than over dense regions with different property, and they're really interesting in the sense that they will we hope they will manage to break the degeneracy. And this is an example of the forecast that we have done in for the Euclid satellite in the omega m sigma 8 plane. Like, so the purple and yellow ellipse are actually the like what we hope to have with different galaxy weak lensing and galaxy clustering constraint on the Euclid satellite. And the blue one is the one that we hope to have with the void size function constraint, so that you see like they are like totally perpendicular. So we hope to break some degeneracy adding the cosmic void into the cosmological recipe. In another end, are really also really interesting in the sense that since we are observing some places in the universe that are by definition matterless, so underdense, they will be like, we are observing zones that dark energy will be much more dominant than in overdense region. So they have been they have shown to be actually really sensitive to modified gravity model. And this is an example of the actually the density profile of void in different modified gravity model, and you see that you can actually see some differences. And finally, and this will be what introduces actually the last part of my talk that I will present before. The voids are also shown to be actually sensitive to massive neutrino, because intuitively, if you are like imagining that the massive neutrino field is much less clustered than the matter field, you will hope to have like, you will expect to have much more massive neutrino in the void region than in overdense region, because of this less cluster effect, let's say. And there, then you will expect to have like the ratio between the matter and the neutrino to be the neutrino and the matter to be much higher, so that the effect of massive neutrino inside which are expected to be larger. And this is what you see here. Basically, these are like two different analyses in simulation. In the first, in the top panels, you see like the void density profile for different at different redshift from one panel to the other, for different mass of the neutrino in the universe. And you see, if you look at the void center, you can actually see that the effect of neutrino can be observed inside the voids. And this is also the void size function. Those are the same function that I was showing you before, the number of void as a function of the radius. And if you look to the larger void, you see an effect of the massive neutrino, depending on the mass of the neutrino in the universe. You will observe much or less void. I will go a bit more in details afterwards on this plot. So yes, so this was the end of the introduction of the void in general, but now I will talk to you about another topic, which is basically the correlation of voids with the CMB. So as we know, the light coming from the CMB will be also lensed by the matter field that it crossed before coming to us. So basically, when you will so you will have this light crossed by the matter field. So looking at specific position in the large scale structure, you can find you can actually cross correlate this effect, and this has been done for the galaxy like widely, and now we can do it with the cosmic void. And this is actually the first observation of this lensing effect of cosmic void by lensing effect of the CMB by the cosmic void that has been detected by in the BOSS data. So basically, this is like similar to what we have with the density profile, except it's projected. So like you can measure actually the position of void, the projected density. So you have like this convergence signal of the function of the radius of the void, like the distance to the like void center, basically. And you see it shows basically the same shape with this compensation wall at the void radius than the density profile. So a bit of methodology. How do we do this? So before starting to the different analysis that I want to show you, I will just explain to you what is this methodology, and I will start with the void finder. So they are like, as I told you, they're like different void finder. I will present you only one, the one that have been used in the different analyses that I will show you afterwards. So this is a 2D void finder, because the 2D void finder are actually are supposed to be optimal to detect lensing signal, in the sense that since they are like projected density field, so you have elongated void, so the signal to noise ratio will be higher. I already told you this before, but good to recap you. So this void finder have been used for the namely in the dark energy survey collaboration. So like the idea behind this, the idea behind the methodology, how does it work? It's basically like this. You have a sample of matter tracers. So it can be galaxy, dark matter halos, dark matter particle, whatever you want to use to trace your density field. You divide your sample in a different redshift slice of a given site. Here will be 100 megaparsec per H. Then in each of the slices, you actually measure the density field by counting the number of galaxies that you have or tracers that you have in a ILPIX map. Then you smooth your density field with a given smoothing scale, which is actually one of the free parameter, like the free parameter of the void finders. So this is like a Gaussian smoothing scale. And then like in your smooth field, you select the most under this pixel, and you start to grow the void around it by measuring basically the density. And once you reach the mean density of your redshift slice, you stop and you go to the second void. And this is an example like a small animation that shows that for the dark energy survey, this was a SV, so science verification data of the dark energy survey. In the background, you actually see the density field of galaxy, like the background color is the density field of galaxy. The dots are actually galaxy clusters, and the circles are the void identified with our procedure. And you see that the circles are actually located in the whiter zone of the whiter regions of the density field, which is showing that we are really identifying this underdense region. So once you have a void catalog, what we need to do is actually to correlate it with a CMB lensing. So what we do is really simple. Basically, we take our void catalog, and at each void position, we cut a patch on the CMB of a given 5 times basically the radius of the void. Then we rescale all the patches, because all the voids don't have the same size, so we have to rescale the patches. And then we just stack them together, and averaging around all the direction, we arrive to this plot that I showed you before of the void lensing profile. So this is the overall methodology of how to do cross correlation of voids, so identifying the void first and then doing the correlation. And this is what we did for the dark in the dark energy survey. So just a quick slice about the dark energy survey. So dark energy survey is a photometric survey that observed during 6 years. It observed about 5,000 square degrees. And so now they are doing the analysis of the 6 years, the last years, the last observation of the dark energy survey. I'm going to talk more about the first and the third year of DS. Yes. So it was located in the South Hemisphere, the Blanco telescope in Cerro Tololo, in Chile. Sorry, it observed through 5 photometric filters, GRIZY, with like this limiting magnitude, and here's like the relative transmission of the different filters, as well as like the picture of the camera and this. So this is a footprint that have been observed by DES. So like so basically what I was showing to you before in the little animation of the void is this little area here. Now I will show you results from the first year of analysis, which is this lighter purple zone here, which is about like 1500 square degrees. And also it's actually year 3 here, like the third year of observation, which is actually the full area of DS of 1000 degree, and that looks at this war engine shape, the total shape. So yeah. So one important thing when you are like doing using photometric observation is a photometric redshift. So like the problem with the thing is like when you are like observing in photometry, then you will have larger error bars in your redshift. You have like more. It's much more complicated to actually define the redshift of the objects that you are observing, and this can also have an implication in the voids that you are looking at. In a dark energy survey, what I've been doing, and this has been what I've been used, and that also been used in the galaxy clustering and galaxy lensing, is actually to define, let's say, optimize photometric sub catalog, let's say, which has been defined with this red magic algorithm that is actually selecting red galaxies that have much less errors for which the redshift is much well defined, let's say. So we had like different sample of this red magic galaxy in DS. We have been using first 2 of them. One is like, because you can play actually in the limiting like in the threshold that which in the luminosity threshold that you are putting. So deciding if you want to favorize basically the density of your galaxy sample or the quality of your redshift that you are using. So we have been using actually 2 of these red magic catalog to identify the void in the dark energy in this paper, which is a first year analysis of the dark energy void cross CMB lensing. So one is a high luminosity sample, so a sample that is much more sparse, but for which the redshift are much better defined. And the other is a red magic high density sample, and as the name says, so it's like the redshift are a bit lower quality, but we have much more galaxy. So the idea behind this paper was actually to probe the methodology that I showed you before. So playing with the different the parameters that we have in the methodology, including the tracer of the tracer of the material field that we use to identify the voids, and the smoothing scale of our void finder to define what will be the best parameterization to have a better signal to noise in our void correlation. So we use 2 different smoothing scale, which are like these ones, like 10 megaparsec per H and 20 megaparsec per H. The two different tracer, which give us in a total of 4 void catalog that are like here. You have them in a different like the different number of voids that we identify in the year 1 analysis. So like this 1500 square degrees of the DF survey. And then we compare it to the mice simulation. So the mice simulation is a simulation for which we also have the red magic that are like, it's specific to death, so like really realistic of the dark energy survey observation. We have 2 we have two simulation of mice. So this is like we compare to the two mice simulation. And this is what we have. So to validate it, we actually, to validate the simulation with respect to the observation, we actually look at different void properties, which are like spotted here, like in this all this histogram. So you have the first line is actually the void radius, second is like the mean density of the void, and the last one is the central density of the void. And we compare all these properties between the simulation and the observation. So the blue one is actually the observation, the decimal one, and the other are the simulation. And we actually validate our void catalog in this way to basically see that the void looks quite alike one with the other. So once we have built our void catalog, we can start to correlate with the CMB. So we have the basic, we have the CMB map from the mice simulation, the conversion, which is the one that I show you here. And for the observation, we use actually the Planck reconstructed map of the CMB lensing. And this is what we obtain. So once, so yeah, this is something that I forgot to tell you, but there's a last parameter that we can use when we stack when we stack all the void in CMB position. It's also possible to apply like, let's say, a filter in the CMB map. This helps us to actually get rid of the small scale noise that we have. So we also prop different filter that we apply to our stacking images. And so here, like each line is a different smoothing. It's a different smoothing that we apply in our stack images. So this is actually only one void sample for like the different mice simulation, mice plus noise. So we add the noise to the mice simulation, and this is a decimal one, and it's like the images that we obtain while stacking. So if you look at the first row, for instance, you see that well, this in the simulation is fine, but once you use the noise, when you apply the noise and when you look at the data, basically, you don't really see behind this the signal. While if you apply the smoothing, then you get rid of the small noise, the small scales noise, and then you can really observe this, let's say, like this blue region at the void position. And like in the right hand side is actually like the convergence profile for each of these images. And if you look at like this line is actually the no smoothing one. You can actually, when you average over like all the direction, you can actually see that you have this signal. But otherwise, by eyes in the images, you cannot really see it. So yes, so we measure the signal for like the decimal one and the mice simulation. We compare them. We look at the error bars and what was the signal. Of course, when you apply a larger smoothing, it means that you will decrease the amplitude of the signal. However, you will also decrease the error bars because you are getting rid of the noise. And then what you can do is actually look at the signal to noise of these different parameterization, and this is the signal to noise that we have. So in average, we had like about 3 sigma detection level. But if we look at the most, we like let's say the best signal to noise that we could have for this parameterization is about 6 sigma. So this is like the one that we actually defined as our optimal parameterization for the detection of such a signal. And then we define this A kappa parameter, which is let's say the amplitude kappa parameter, which is basically the ratio between the convergence signal of the observation to the mass observation. So let's say the agreement between the two, and we see that most of the different parameterization actually shows a agreement that is actually in agreement with one. So like simulation and observation are quite in agreement. So we then the year 3 analysis arrived, and we could reproduce the same analysis using so the optimal parameterization that we had defined before. So now we are like in 5,000 square degrees, so much more larger area. We did this for the void that we again compared to the mice simulation. But we also basically reverse the void finder processes in order to, instead of identifying under the city, we also identify like over density. So it's like not kind of super clusters. They're not like the same thing that cluster because they're not viralized, but they're like this really large over density region. And this is the result that we get with this in this analysis. So like again, in the left hand side, you have like the stack images of the void the void correlation with the CMB Planck and mice map, basically for the voids and the supercluster. And the right hand side, you have like the profile of these images. And quite interesting, if you look at the profiles, both for the supercluster and for the void, like the error bars, like they say the like dark error bar, like dark blue error bars or dark red error bars are actually the one observed by the dark energy survey, while the light one are actually the one in mice. And if you look at the center of the structures, you see that you have a small disagreement between them. It's like about like 1 to 2 sigma. It's not large. It's just the error bars are quite large, but it's quite interesting, and we are like working on it to understand. Another interesting thing is this small disagreement between observation and simulation has also been observed recently in a dark energy spectroscopic instrument in a legacy survey of DESI, basically in different beams. If you look at this, these are like different beams in redshift. You see that you have like a small disagreement between the two. We try to basically divide we try to basically identify a subsample or subpopulation of voids that actually are more affected by this, are more like, let's say, in disagreement with the observation, but we were not successful. So basically we divide our void sample in different void radius, subpopulation, redshift, density, and so on. And we look at this same aka amplitude or like agreement parameter with the simulation, and we see that like basically they all show this the small disagreement with respect to the simulation. So what this disagreement show basically is that the correlation of a signal of the voids or the supercluster with the CMB seems to be smoother than the one in simulation. So the voids or like the large structures seems to be less clustered than than in a simulation. That's what we simulate. So I'm not going to go through that because I don't have much more time. So that's where we start this analysis that have been published like last year, basically. I mean, this at the beginning of the year, which like the idea was to try to understand what would be the effect of massive neutrino in such correlation of void with a CMB. To understand if like the effect of massive neutrino could actually explain this small discrepancy that we have. So for this, we use the Demuni simulation. So the Demuni simulation is a set of n-body simulation that present different cosmology, and more in particular, it offers us the opportunity to work with massive neutrinos, since he has different simulation with different mass of the neutrino that you have here, but also it provides us the different CMB map, and more in particular, the one that we are interested in is like the ray tracing CMB lensing map from the simulation. So just a quick introduction of massive neutrinos. So what massive neutrinos are doing in cosmology. So basically, the massive neutrino at small scales, they are like relativistic particles. So they will basically travel through the matter field, smoothing it. While if you go to larger scales, they will act like a non-relativistic particle, so as matter, so they will basically fall in a potential wall. And this scale, like let's say the change in scale is led by this free skimming scale equation of the massive neutrino, which you have here, and that of course depends on the redshift that you are like considering, and also on the mass of neutrino. And this is like a plot of the evolution of this free skimming scale divided by the scale factor, so the co-moving free skimming scale of the massive neutrino as the function of redshift for the different mass of the neutrino considered. And here on the right-hand side, I put you basically the power spectrum or the CLs of the kappa kappa. So it's like the CMB lensing convergence CLs of the diminished simulation for different mass of the neutrino. And if you look at the larger hairs, so the larger multiples, the smaller scales, you see that as you increase the mass of the neutrino, you tend to decrease the power spectrum. So you basically smooth the smaller scales while you are increasing the neutrino. And what is interesting, if you go back to the first plot, is that like if you look at the y-axis of this plot, is that you are like in a basically 20 to 1 or 200 megaparsec per age, that we are like in the same basically order of magnitude of the scale that we have in our cosmic void. So the cosmic void are basically typically the size of this free skimming scale of the neutrino. And that's why they're supposed to be quite interesting also if you want to study or to put constraint on massive neutrino. So, so we start this analysis in the different icon of the diminished simulation with different mass of neutrino. And the first thing that is important is that since we are using different simulation with different mass of neutrino, we will use different tracers. So in this case, we use only the halos, the dark matter halos of the diminished, because we don't have the galaxy yet, but this is the same idea. But while you are increasing the mass of the neutrino or changing the mass of the neutrino, you will also change your tracer. And this will have an impact in the void population that you are like identifying in it. So basically, we look at the halo mass function, which is basically the number of halos that we have at a given mass for the different simulation of the different diminished simulation with different neutrino mass. So this is a halo mass function, the function of redshift. So the different color are different redshift, and the different lines or markers are actually the different neutrino mass. And what you are observing is that, again, the massive neutrino tends to actually smooth the matter field. So basically, when you add the neutrino, you will form less structure. So you will decrease the number of really large halos. And of course, as you increase the mass of the neutrino, as this difference is much pronounced. This is what you have like the difference between them for the different neutrino mass in the bottom plot. So we had our this halo catalog basically, and we identify the voids, and these are like actually a plot of like the different voids identifying in one redshift slides of the diminished simulation. So for this analysis, we use 3 different smoothing scale in our void finder, which are namely this 3 one. So we had like a larger smoothing scale with respect to the dark energy survey one. What we see, this is like the number of void identified for each of the neutrino simulation. What we see is that as we increase the mass of the neutrino, we tend to decrease the number of void. And this makes sense in the sense that as you increase the mass of the neutrino, as we see in the tracer before, you tend to decrease the number of halos that we identify. So like you decrease the density of your sample. So it means that you will tend to identify voids that are like, or structures that are much more larger, but less of them. So like less void, but well, less numerous, but more larger. And this is yes. And then I have this slide to explain, like to give you an example of what actually is like this smoothing scale in the void identification that I keep on talking about. So basically, the idea beyond the smoothing scale is like to erase like the small scales fluctuation in your density field. So as you go to higher smoothing scales, you will tend to identify like voids that are much larger but more smoother. So this is an example from 10 to 30 smoothing scale in the void identification. So basically what you are like, this is exactly the same slice with a different smoothing. So the same galaxy catalog that you, or halo catalog that you have actually in the background colors. And as you increase your smoothing scale, you see that the structure seems to be smooth. So like you will identify voids that or identify structures that are like much more small and underdense in the smaller smoothing scale, that when you go to larger smoothing scale, you will tend to identify much more like, let's say, less underdense but larger void. And this is this is quite important for the future, for after. And these are like the void size function of our void in a de Minimis simulation. So basically what you see, like these are like the different smoothing scale. What you observe there is like, if you go to the smaller smoothing scale, it seems that the mass of neutrino is much more important, like decreasing the number of void or the number of small voids basically. While when you increase the smoothing scale, it seems that this difference is much lower. But this makes kind of sense because the effect of neutrino is actually similar to what we expect to, like, the smoothing scale itself is doing. Basically, the neutrino will tend to smooth the matter field, so like to have the exact same effect that what we have when we are doing the smoothing procedure in our void identification. So if we look at the larger smoothing scale, it's like the same thing than implementing neutrino in our simulation. So like the difference between the void size function of the void identified in both in the different massive neutrino simulation won't differ that much, basically. So then we look at the, like, this is a density profile of void. So this is basically the 2-point correlation function of void with the halos in our simulation. And if you look at this 2-point correlation function, so you have this underdense region at the void center that goes to the that goes actually to the mean density of our sample. For the different massive neutrino simulation, if you look at the void center, you see that this is only one smoothing scale. But anyway, if you look at the void center, you see that the lambda CDM1, which is like the massless neutrino 1, here seems to be a bit smoother, like less underdense at the void center. And this is quite interesting because in principle, when you add massive neutrino to a simulation, you will expect to have the opposite, right? The effect of massive neutrino tend to smooth the clustering, so you will expect to have the like lambda CDM1 to be much deeper, than the massive neutrino one. However, it's not what we observe. And this is like a, let's say, a observation artifact, in the sense that we are observing dark matter halo, and here we are counting the number of halos which are like bias objects of the matter field. So basically, when we are we are limited also by the simulation, so we are not observing all the halos because we have of course let's say a limit in the minimum mass of the halo in the simulation. So we are not counting all the smaller halos, which are much more present in the density in a lambda CDM which are much more present in the massive neutrino case, due to the fact that the halos will be split due to the smoothing effect of the massive neutrino, or to the less cluster massive neutrino simulation. So basically, because we are doing this, looking at the dark matter halo, which are like biased, and also we are limited by the resolution of our simulation, we are observing like completely the opposite effect that we will expect in the matter field, in the overall matter field. And this has been And this also I've been observing this in this paper, that this is actually measuring the effect of like the density profile of cosmic voids for different massive neutrino mass, but this time in the directly in the dark matter particles. And you see that as you increase the mass of the neutrino, this time you actually recover like a smoother large structure. However, I mean, when we are doing correlation with the CMB, we are not expecting to be biased like this, because we are observing directly like the lensing signal, which is not, so it's like the ray tracing of the dark matter particles in the simulation, but so we are not limited by the resolution of the simulation, is the bias, because we are not biased by the object that we are looking at. And so this is actually the result that we have of the correlation of the CMB with our voids for the different smoothing scale that we use in simulation. And if you look, let's say in this case, which is much more that we can see much better in the void center, this time you see that the lambda CDM, so the massless neutrino simulation, is actually much deeper. So so like the massive neutrino tend to smooth the matter field as we expected. And this is like we define this parameter, which is a sensitivity parameter, which is a bit an analog to the AK parameter that I showed you before, when we were like comparing the dark energy survey to the MICE simulation one. But this time we compare, like we do the ratio between the massive neutrino to the massless neutrino one signal. And this is like basically the value of this sensitive parameter as a function of the smoothing scale. And you see that as you increase the smoothing scale, you tend to have like much more smooth signal. And this is quite interesting, is that if you go back to the dark energy survey observations and compare that to the MICE simulation, it seems that it's completely in agreement, in the sense that the effect of massive neutrino in this correlation is actually to smooth the profile, the stack profile of our void that we observe here. So if we look at the void center, like the stack profile of the dark energy survey is actually a bit smoother than the one of the MICE. So we can so basically, if you add the massive neutrino in the MICE simulation, you will tend to put all this error bar a bit upper. So it goes in the same direction. And and I think I have a bit more of time, but not much more.
If you can finish within 5 minutes, so we can have a bit of questions, that would be perfect.
I'm almost done. So yes, and so lastly, what I want to comment is about like this, as you go to larger smoothing scale, what do we observe much more? Because if you go to smaller smoothing scale, then you don't observe this. And this is just because it's a nice image. So basically, again, on the smoothing scale, so this will be like when you observe, like you identify void using a large smoothing scale in your void identification procedure. So in this time, you will basically identify this void, which is like, let's say, large, and also you will see that in the middle of the void you still have like you have basically structure inside the void. However, when you decrease the smoothing scale, you will divide this void in a different void with less structure inside. And if you go to smaller smoothing scale, we do the same. And this is exactly why when you go to like, if you're like looking at this kind of voids, you have like all the structure inside. And this structure actually the one that will be much more affected by the presence of massive neutrino. And this is actually why when you're like observing to large structure or large smoothing scale, basically you will have much more effect due to massive neutrino. And this is quite interesting for future survey in particular. And these are my conclusions. So basically, I hope I convince you that voids are like actually a new promising tool to do cosmology with massive neutrino and modified gravity and so on. We have shown that like when we add the massive neutrino in our simulation, we tend to smooth our void lensing signal correlation with the CMB, and this is quite interesting in the sense that it goes in the same direction of the small tensions that we have in DES and DAISY observations with respect to simulation. And of course, the presence of massive neutrino will depend on the scale. So the scale that we are observing and the redshift considered. So I refer you to the paper, to the Demuni paper to see more details. There are like much more plot and analysis on it, but I didn't have time to show all of them. If you're interested, go there. And that's basically everything that I have to say. Thanks for listening. And we can have questions now.
Thank you again for a nice talk. Is there any question? If not, I can start the discussion. So you mentioned at the beginning that there's several ways of defining voids. Either you look at 2D voids and in slices of redshift, or you go for 3D. But it's not clear to me exactly why the 2D approach is better than the 3D, because I would expect that the 3D would be more sensitive to the lensing, to the matter distribution in that 3D sphere. Is there an intuitive way of understanding why the 2D definition is better?
I mean, better. So there are different. So for the lensing, it's better in the sense that it gives you more signal to noise. Better in like if you want to do theoretical approach, it's much more complicated. So it depends what you want by better. Then for the lensing, it gives you better signal to noise in the sense that you are like observing like really elongated objects. So like in a line of sight, the voids will be larger than the 3D. I don't know if I can draw something here. In principle, you have something to draw, no?
Yeah, you should be able to.
Does it work? Yes. Right.
Yes.
You see.
Yes.
So basically, I don't know where to do this. Basically, imagine you have like a slice like this, and then you have the deflection that coming from the galaxy there. If you have an object that is, I'm not very good at drawing, but if you have an object like this, you have less deflection if the light goes there, right? Well, if you have an elongated object, then like the deflection will be like stronger. So it's not my best draw in my life. but yes, I mean, it's just a matter of like the fact that the object will be elongated, so you will have more signal. So it will increase the signal to noise. Then better is a big word. I don't know what is better. It's just you have more signal.
Okay, so I have a couple of other questions, but I will let Uyan go.
Right, thank you for a really nice talk. I'm quite new to this field of cosmic voids, so I have a somewhat naive question. I was wondering, when you're explaining the void catalogs, the way you find it, there's some critical density that goes into finding these catalogs, that you grow your mean density until you hit the critical density. So I was wondering, for overdensities, there are some like simulations and a magical number for this overdensity, like critical density in some way. But I was wondering if there's such equivalent number for like a natural number to choose for this mean density threshold, and whether if this number would affect your final like cross correlation results quite a lot, depending on if you change this, it might change the void catalogs and also change your cross correlation result.
So you mean so basically here, like when you identifying the voids, you stop to grow the void at the mean density, and this is what you call by the critical density.
Right, yeah. So maybe I misunderstood, but there are some critical density.
Yeah. So
threshold density rather. Yeah.
Yes, in this void finder, you actually choose to stop to grow your void in at the mean density of the slides that you choose. If you change that, it won't affect much the because when you're like doing the correlation with the CMB, you are stacking. So this basically, you, for instance, in this slice, you will observe like this void will be observed, and instead of let's say like you reduce this mean density, you say like, okay, I just want to grow my void until like one half of the density of the slice instead of going to the mean density of the slice. So in this slice, for instance, you will observe like this void will go just don't grow further here. Maybe you will observe other void here, but probably not, because you are not because you also have like you need like a very underdense pixel to start the void. So basically, you will just, I guess you will just rescale your voids instead of well, you will have a bit more void, but I don't think it will be significant. You will just rescale your voids, so you will have smaller objects. And then when you do this, the cross correlation, you also rescale it. So probably it will affect your profile a bit. The profile might be probably a bit stronger, but I'm not sure it will be that strong in the middle, because in the center of the void will be the same at the end. But,
right, I think I found my misunderstanding. So it's growing until the mean density of the slide itself, I guess, not a certain like a number. So yeah, but it's interesting. I'll read into more. Thanks for answering. Yeah.
welcome.
If we have time for one other question, if there's any. So yeah, I had a question because when you showed the forecast for Euclid, it's quite interesting to see, as you show, it's perpendicular degeneracy direction, so you can break this using voids. So my question is, what can you say about sigma 8 and omega matter using these techniques? You didn't show any constraints using real data, so I was wondering if it's possible.
You mean using the cross correlation, CMB cross correlation?
Yes. Can you put constraints on this?
So in principle, yes, but the issue with void, and we are working on it, is quite difficult to have a theoretical prediction of the void profile, as I show you, and this is quite important to actually do. I don't know where it was. And this is quite important to have a theoretical prediction to actually do a cosmological constraint. So as everything in cosmology now, you have two ways. Either like you actually find a theoretical prediction, or you build an emulator. We are working in both of them, but for CMB, I'm working personally in in the void lensing with Galaxy, but then it will be also extend to the CMB, and this is an idea for, well, more Euclid than DAISY, but the Euclid LSST to actually have something that put constraint on the omega m sigma 8. But so far, what we have been doing and what has been done is comparison to simulation to see if it's consistent. And if the question is, do we expect it to be also perpendicular in the sigma 8 omega m plane? No, I would say yes, because I want to sell the voids, but I don't know.
Okay, interesting. Thank you. If there is no other question, maybe we can stop the recording.